Hello everyone. I am going to go over an example that is from OpenStax Calculus Volume 1, Section 5.2, Double Integrals over General Regions. So OpenStax is an open source book. It's free for us to use because of a foundation generously funded this, and I'm going to do a problem here. I don't make any money off the video, so it's in spirit of open source. All right, we are going to do a double integral over a general region. If you look at any multivariable calculus book, then you'll see this topic. So maybe also it would be nice if I wrote over here multivariable calculus. That's what this is. So this is a topic from multivariable calculus. So if you wanted to further search that, go to this Calculus Volume 3 book also that can be found at openstax.org. All right, so let's look at this problem here. And what we have is we have an integral over a function which is possibly thought of as volume over a region D. So if I were to sort of waste some time, but not necessarily, because I don't think it's total waste time, but if I were to draw the three-dimensional picture here, I have a region D that's in the XY plane. And so this picture I'm drawing doesn't really necessarily help anything, but I'm still going to draw it. Okay, so you have this region D that's in the XY plane, and so I'll sort of make a rough sketch of that. And, you know, it's a triangle, and looks like I got it somewhat right. Okay, and I'll shade that in. Okay, so that's a region D down there. And what we're looking at is a surface that is lying above the region. Now, the thing is that I'm not doing at all is trying to draw this surface at all. I didn't even think about it, except I do know that x squared is never negative. It could be zero though, you know, actually, so, no, actually, that's true. At the origin, it's zero. So the surface probably looks more possibly like this or something. Oh, well. So it's zero, the surface is zero. So maybe it looks possibly, you know, maybe something like this. Okay, so here's our surface sitting up here. And then what this problem is doing is finding the volume, you know, the volume underneath that surface. So actually, now that I'm thinking about it, I mean, this is not in the solution in OpenStax, but you could find this little point here. See, this point here apparently is x is 2, y is 1, and z is 0. But you could plug in to find this point up here, which by putting an x is 2 and y is 1, and it looks like I would get 4e squared. So, you know, this isn't to scale. 4e squared is about 4 times 3 squared, so it's around 36. Anyway, but yeah. So anyway, but that's without having a picture of this to scale. One way to interpret this is the volume beneath the surface. But that picture is not provided for us, and you know, we're not trying to sketch the graph well, and I maybe might be disqualified by some people for drawing such a you know, a poor quality approximation of this, you know, of this surface. Anyway, that's D there. All right, now D is what they call a type 1 region, as they say, as it says right here. And we're going to evaluate this over the domain D. What does type 1 mean? It means that the region D is bounded by two functions, one on the top and one on the bottom. And those are both, what I mean by function, I mean y is a function of x for both the top and the bottom. So what I like to do is I like to write down D in set notation, and someone was saying that they are a little uneasy about set notation. You just sort of describe the describe the set D, but you put squiggly bars around it. I mean, it's a little bit more than that, but not much. But it's the set of all, the squiggly bars mean set. So the squiggly brackets. So the set of all x, y, and this vertical line means such that. Some people prefer a semicolon. Why? Because the vertical line means something in probability, so you might not want to do that. Okay, so you can do a semicolon. Such that x is between 0 and 2. But by the way, I usually do vertical bar in this class for multivariable calculus, but I'll just do the semicolon. And then y is between 1/2 x and 1. So see, these are our two functions, except I wrote it down wrong. So we have two functions. This function, the y is greater than, is on the bottom. I mean, all the y, if I put a y coordinate in the set, that y coordinate is, the y value is greater than the y value on that blue line there. And that blue line is given by y equals 1/2 x, but it's less than the value on the red line, which is 1. Okay, so that helps me when I write this integral down, the integral over d of x squared ex to the y power dA. It helps me to do the set notation of d. If I don't have that, I often get everything wrong. So x is between 0 and 2, and we always put the bounds, the integral, the bounds that are numbers on the very outside. I put parentheses like this, so that means on the outside. 0, 2 is the last thing I'm going to do. I'm going to integrate that, and that's with respect to x, because x is between 0 and 2. And then I'm going to integrate between y equals 1/2 x and y equals 1, and then I'll copy and paste this e to the xy, and I'm integrating that with respect to y, because y is between 1 and y is greater than 1/2 x and less than 1. Alrighty. By the way, I mean, sometimes if it seems confusing, why not write x equals 2, x equals 0? Just to keep in mind that these are x values. Y equals 1, y equals 1/2 x. You could do that. That's a little mess to the problem. All right, now, when we integrate with respect to y, this x squared is a constant. So this is partial integration. So we're just going to integrate with respect to y. Before I do that, I'm going to write down an aside and just remind ourselves that this e to the k times y, k being a constant dy, is equal to 1 over k e to the ky plus c. Well, to really get into it, you can use substitution where u equals ky and proceed that way. But it's sort of a simple, it's sort of a simple integral. We know the integral of e to the y is just e to the y plus c. So what happens if you have ky? Well, one thing is, let's just note that if I take the derivative of e to the k times y, I use the chain rule, and I write down e to the k times y, because the derivative of e to the u is e to the u, and then the derivative of ky is k. And so to check that this is actually the correct integral, take the derivative of e to the ky. It's k e to the ky. Then we multiply by 1 over k. So 1 over k and k cancel out, and we get this above here. All right. So as you can see, this is slow going. I'm making little explanations along the way, but the idea is that it's going to help. Okay. So on this particular problem, then, I'm going to get still 0 to 2, and then I'm going to integrate. I have x squared. In this integral, e to the xy, x is, corresponds to k. And so the integral will be 1 over x e to the xy. And then I'll evaluate putting in y equals 1/2 x, or even x over 2, if that looks nicer. Y equals 1 dx. Alrighty. And of course, we have a little bit of cancellation with x squared divided by x is x. And now I will go ahead and plug in y equals 1 first, and then y equals x squared with subtraction. So it's going to be e to the x times 1 minus e to the x times x over 2. So things are really getting exciting and pretty darn fun here. Okay, so x times e to the x, I get x e to the x minus x e to the x squared over 2. And then what's sort of pretty good about this problem from OpenStax Calculus Volume 3 is that we have to practice our integration here. We have a little bit of a challenge to integrate here. I'm going to call these A and B, and what I'm going to do is just on the side is evaluate the, here's A, I'm going to evaluate the indefinite integrals on the side of the page. Like here's x e to the x dx. Okay, this is a classic integration by parts problem. It's not even the most difficult. It's sort of like the beginning integration by parts problem. And so integration by parts says that integral u dv equals u v minus integral v du. So you have u here, and what you do is you take the derivative of that u. So here's x. When you take the derivative of x, you get 1. So that's the one you let u equal. Because derivative, so you have du equals 1 times dx. So you don't have the x anymore. On the other hand, you can let dv equal e to the x dv, and you find the antiderivative, and v equals e to the x. And then we multiply, as it says here, u times v. So that's x e to the x minus integral, right here, v du, integral v du. Well, v is e to the x, and du is dx, alrighty. And then the integral of e to the x is just e to the x. I'll put plus c1, even though I'm going to use this in a definite integral, but I'll do that anyway. So, okay, let's go on to b. B is also sort of a classic problem. By the way, you can find the solutions in the OpenStax textbooks of this example. They have that. I'm showing a few more details, but it's pretty awesome there. So, okay, I'm going to write down B. Now, what I did, I did this problem on my own before doing this video, and I made a mistake because I did B, but I didn't put the negative with it. And then when I added these together, I'm gonna integrate these individually, then put them together. But then when I want to make sure I get that minus, just pointing that out. So I put the minus there just to make sure I don't lose that along the way. All right, this is a classic substitution problem. Here's x squared over 2, but we know the derivative of x squared is 2x, and boom, there's x right there. So I'm going to let u equal x squared over 2. The derivative of u is 1 du, and then for x squared, that's 2x, but then we divide by 2 there. So du is equal to x dx. Alrighty, and if I'm really super patient here, often not, but let's say I am in this case, I can put the x right next to the du so I can see that x dx, according to what I wrote here, is du. X squared over 2, that's u. Alrighty, don't forget the negative, otherwise we'll get the wrong answer. E to the u du, and that integral is negative e to the u plus c2, which is negative e, no, it's u is x squared over 2, plus c2. Okay, so these are like little partial, or little getting there solutions, but of course, those were just the indefinite integrals, and we're going to add them together. So our answer then is the sum of these, x e to the x minus e to the x, plus this one right here, which is plus adding a negative, so I'll put negative x squared over 2. And then I'm going to evaluate from 0 to 2. Those are our bounds of integration. And, you know, at this point, I could get the wrong answer only by just not focusing, because it's definitely not advanced math for me to put 2 and 0 in. So let's do that. So I'll put 2 in for x, e squared minus e squared minus e 2 squared over 2. Then I'll put in 0. 0 e to the 0 minus e to the 0 minus e to the 0 squared over 2. All right. So this makes 2e squared, obviously, I'm just copying and pasting, minus e squared. And then 2 squared is 4 divided by 2 makes e squared. So, interesting enough, the plot thickens. This becomes is 0. 2e squared minus e squared minus e squared, that's 0. Then we have 0 times e to the 0, that's just 0. And then e to the 0 is 1, e to the 0 is 1, so we have minus 1, minus 1. So this gives 0 minus negative 2, which is 2. Well, did you see that coming, that you were going to get an integer as the final answer? I might have thought it might have e or something like that, but that's a pretty cool problem there, that after all that, we get 2. Again, I was drawing this little rough sketch. It's of the surface. It's not even. It's not very good. Okay, but it really isn't that good. Well, it's not that bad, but it's not at all the scale. Like I said, you can easily see that this corner is around, has a z-value about on 36. But anyway, no, should I say anyway, or go make it better? But anyway, that's not what they asked for. But I was just trying to point out that what this is this is the volume of the solid of the solid. This is the volume of the solid region under this surface, found by z equals x squared e to the xy. It's the solid, the volume of that solid over this triangular region, which is, d here, and turns out the volume is 2. All right, well, it's pretty great. So okay, so maybe I went through that too quickly, and let's take a look at that more. Let's just zoom out, not too much, but so I guess what I did that's more than if you just look at the answer in the book, is I went through each of these integrals, the integration by parts and the integral by u substitution. Let me make clear that this is u substitution. So it's a good problem because it has both a review of u substitution and a review of integration by parts. Alrighty, well, you can always do a like if you'd be kind enough to do that, a like, a comment, and click to subscribe. So, but I'm not making money off this. This is all for public and education and open source. Alrighty, awesome, thank you.